On this example, we're going to go through several things: finding the domain intercepts asymptotes, intervals where increasing, decreasing, and local maximum minimum, and then the intervals where it's concave up, concave down, along with the inflection points. With this information, we're then going to sketch a graph of the function. So let's start with the first step. In this particular example here, it's the f of x equals x to the fourth minus 2x to the third, and we're going to do the domain. Now the domain is a pretty short step on this one. Since this is a polynomial, the domain is all real numbers. Okay, and so we don't really have to do anything else there. On the other hand, when we talk about the intercepts, we need to find the x-intercepts and the y-intercept. To find the x-intercept, we're going to set the f of x or y equal to 0. So the x to the fourth minus 2x to the third, that's all going to be equal to 0 here for the x-intercepts. And we'll solve by factoring out an x to the third, right, as x to the third times x minus 2 is equal to 0. And when we set each of these factors equal to 0, x to the third equal to 0, x minus 2 equal to 0, we'll get two numbers. X is equal to 0 and x is equal to 2. And those are the x-intercepts here. For the y-intercept, we'll plug in 0 for x, which in this case just goes 0 to the fourth minus 2 times 0 cubed, and it's just 0 also for the y-intercept. Now, as far as asymptotes go, there are none for this particular function because, again, it's a polynomial, and polynomials don't have asymptotes. For the step of increasing and decreasing along with the local max and min, what we need to do is first off find the derivative f prime of x. For this function, the derivative would be 4x to the third minus 6x squared. We need to find what's called the critical numbers, which we get by taking the derivative and setting it equal to 0. Technically, we also check where it does not exist, but it would always exist in the case of a polynomial. So we just need to solve it equal to 0. Here we can solve it by factoring out the GCF of 2x squared from both terms. Write it as 2x squared times 2x minus 3, all equal to 0. When we set each factor equal to 0, 2x squared equal to 0, 2x minus 3 equal to 0. In the case of the first factor, you could divide out the 2 and write it as x squared equal to 0. However, even trying to take the square root to both sides still just leaves it as x equal to 0 here. On the other hand, when we solve this other factor equal to 0, 2x equal to 3, divide out the 2, x is equal to 1.5. Now what we do with these numbers is we're going to imagine them on the number line, and we're going to choose some test values. So the test values I could choose here are numbers like -1 on this side, +1 in the middle, and 2 over on this side. We're going to check to see the intervals and see what happens by plugging in these test values into the derivative. The interval from -infinity to 0, 0 to 1.5, and 1.5 to infinity. If we start by plugging in the -1, it would look like 4 times -1 to the third minus 6 times -1 squared. Again, I'm plugging that into the first derivative f prime of x to see if it's going to be increasing or decreasing. I came out here with -10, and since it's a negative number, it's going to be decreasing over in this interval. Now if I plug in +1 for x inside the derivative, it'll actually come out to be -2. So it's actually still negative here, still decreasing. Now if we plug in 2 for x inside the derivative, let's see what happens then. It comes out to be +8. So now since it's a positive number, this part will be increasing. So what we'll say here is that it's increasing on the interval from 1.5 to infinity. It's decreasing on the interval from -infinity to 1.5. Then, after we do that, we'll check local max, local min. If the graph goes down and then comes up, that's the case of a local minimum. If the graph goes up and then comes down, that's the case of a local maximum. In this case, we have it go down and then up. So that'll be the case where we have a local minimum here at 1.5 for x. So let's write down the point x comma y for the local minimum. X is equal to 1.5. Y is equal to, go back to the original f of x function and plug in 1.5. In this case, that'll look like 1.5 raised to the 4th minus 2 times 1.5 raised to the 3rd. I came out with approximately -1.7 for that. So the point is 1.5 comma -1.7 approximately for the local minimum on this one. The next part we're going to do involves the concavity. To do concavity, we need to find the second derivative, f double prime. Keeping in mind that our derivative f prime of x was 4x to the 3rd minus 6x squared. So the second derivative would go 12x squared minus 12x. And we need to use that to determine the concavity. We're going to solve the second derivative equal to 0. So 12x squared minus 12x equal to 0. We can do that by factoring out 12x and write it as 12x times x minus 1 equal to 0. If we set each of these equal to 0 here and solve for x, we'll get out solutions of x is equal to 0 and x is equal to 1. Just like with the first derivative, we're going to set those up on the number line, and we're going to choose some test values. Test values we could choose here are numbers like -1, 0.5, and +2, let's say. We're going to be substituting these numbers, test values, into the second derivative, so the 12x squared minus 12x. If we start with the -1 and plug that in, it would be 12 times -1 squared minus 12 times -1. That's going to equal 24. Since that's a positive number from the second derivative, it's concave up. If we check that with the 0.5 in the place of x inside the second derivative, it comes out to be equal to -3. So now a negative number means that this will be concave down inside there. And then lastly, if we check with the number 2 in the place of x, we'll come back out with +24 again. Positive and concave up. So we're going to say that this thing is concave up on the interval from -infinity to 0 union 1 to infinity. It's going to be concave down in the interval from 0 to 1. Now the points where it changes concavity, the 0 and the 1, are what we refer to as inflection points. So the last step here before we draw the graph will be to write down the inflection points. So we have one inflection point for x equals 0. And if we want to know what the y-coordinate is, we'll plug that back into the original, not derivative function, which will equal to 0 to the 4th minus 2 times 0 to the 3rd, and that's still just 0. So one of the inflection points is 0, comma 0. And then we have another inflection point for x equals 1, and y would be equal to f of 1, 1 to the 4th minus 2 times 1 to the 3rd. That would be equal to negative 1. And so the point 1 comma negative 1 is also what we refer to as an inflection point. Okay, now to put all this together, let's start with our intercepts, which we had an x-intercept and also y-intercept at the origin, 0, comma 0, and also an x-intercept at 2. And then we had a local minimum at the point 1.5, comma negative 1.7. So let's kind of put it somewhere in here. We had an inflection point located at the coordinate of 1 comma negative 1. So right in there. Okay, and now we're ready to sketch this. It starts with a concave up part, and then it switches to concave down, and then it switches to concave up, and looks something like this.